Okay, so here's a schematic that I found in an online resource and also in Horowitz and Hill that is just a modification of the previous circuit that was the PMOS, or excuse me, the P-type BJT transistor current source. You can see it on the previous video up here. But this guy just uses an op amp to also to stabilize the voltage across this resistor and get a constant current flowing. So let me just show you how that works really quickly. What the Zener diode does is establishes a constant voltage between this node and the rail. And in this case, the voltage drop across the Zener is, well, we'll just call it VZ, but it's about 5 volts here. So say VCC minus VZ here. And so how does that translate to regulating the current through this wing? We want to regulate the current through this device under test. Well, if you remember from very high level op amp discussions, the op amp changes output as to try to keep these two inputs at the same value. And so if we set the value at this guy, then the output of this transistor, the output of the op amp is going to change such that this node is equal to this node. And so what would that mean? If VCC minus VZ is on this node, then it's also here, which means it's at the emitter. And so what that means is then the voltage drop across this resistor here is going to be VCC minus simply VCC minus VZ, and that's equal to just VZ. And so then it's very simple to see that the current flowing through this emitter, and the approximation is also that since the base current is low, that's IL, or I guess we'll call it IE, is the same as IL. And it's easy to see that that is simply VZ equals ILRE. So your IL is just VZ over RE. Okay, here it is, just not that interesting. We have the PNP here, the diode, basically the Zener, reverse bias Zener diode on this side, and the op amp. We're just using 1/4 of this LM324 op amp. And so let's go ahead and see what its performance characteristics are. Okay, so as you can see, we got, I'm probing the voltmeter on the diode resistor junction, basically on the input to the op amp, and that's a 5.25. So that means that if we're at a 10 volt rail, so 4.75 is the Zener voltage drop for whatever reason. I thought it would be 5.3 as the data sheet shows for the 4377 Zener, but and we have a 2.2 kilo ohm resistor going into the as the emitter resistor, and so 4.75 volts divided by 2.2k is about 2.16, and we've got 215 here on the ammeter on the collector of the transistor. So that is working, and working as expected. Now what I want to do is instead I'll probe the rail, because again I want to check now the dependency on the supply rail voltage, the dependency of the current on the supply rail voltage. So I'm going to go ahead and change this guy with my buck converter. So we got, let's say we go up to 12, we're up to 12 volts, and we've gone about 0.0, just, okay, it's flickering between 17 and 18, but about 0.02 milliamps change. So that there is about 0.01 milliamps per volt on the supply rail. And it's a little bit more if I go down. We were at 16 down to 8, so now we've gone about 0.05. So it's between, it's not linear exactly, but it's between 0.1 and, at least for the range I just checked, it's 0.01 to 0.02 milliamps per volt. So yeah, it's not immediately obvious to me what we've gained by changing it to this certain configuration. One thing it does make it easy to do is this op amp has now locked down the base voltage of the PNP transistor. And so what we can very easily do is make a current mirror. For a current mirror, all we're going to do is also connect this output to another, hopefully identical, but of course not always exactly identical, transistor with its own emitter resistor, just like this. Okay, so then for any subsequent branch of this current mirror we want to solve for, we just simply divide the V-Zener by the emitter resistor, and that gives us the current. We'll call it I2. So, if the resistor is double, then you're going to have half. If it's double the original resistor, then you're going to have half the current that was going through this wing. So, pretty simple. Let's go ahead and take a look at this. Okay, so we got the second transistor, same component as this one, also same resistor. I'm just going to go ahead and mirror the exact current, the exact same current. So this is another 2.2K, which sure enough, it is 2.15. So that is exactly the same current that we were drawing. I mean, obviously these resistors aren't the exact same. There's some tolerance there, but they appear to be close enough that we have the same current through these two guys. So that's pretty cool. We are going to now use all these concepts with diode curves and current mirrors, constant current sources, to make a diode temperature sensor.